Okay, so today's section 4.4, as you can see, it's called Curve Sketching Techniques. The good news is a lot of this you've already had, but this is sort of the section where we wrap everything up. So we've done all the stuff with first, second derivative. Just recently we did the thing with the end behavior, the asymptotes and where it goes. And then in this chapter, we're just going to kind of tie some loose ends and kind of get it to the point where you should be able to graph just about anything precisely using these techniques. So that's where we're going today. So like always, I'm going to go ahead and just do a little bit of not many PowerPoint slides. So I'm going to go through these though, and then we'll talk about some problems here and go over some homework examples for you. Okay, so we talked about asymptotes. We talked about horizontal asymptotes last time, and that was, again, where the graph finishes as you go toward infinity or toward negative infinity. So they omitted them, but they did talk about them a little bit here. They just didn't talk about the graphic. Okay, so what's going to happen is, as you can see here, polynomial functions do not have asymptotes. Rational functions can have them. And polynomial functions you might find might have some other types of asymptotes, and we're going to get into that here as well. So, little reminder here, rational functions can have them, and just a couple of examples. Rational functions may look like this, these types of graphs, where you have a horizontal, I know that's bad, and you have a vertical asymptote right there, so that's a typical rational function. Log functions and exponentials, same thing. For exponentials, you're going to have a horizontal asymptote. So an exponential function typically looks like this, where there's one asymptote, but the other part continues to kind of go on upward here. It doesn't really stop. There's no vertical asymptote. So again, that's exponentials. And then logs, on the other hand, it's kind of the exact opposite, where there's a, lost my picture here. There's a vertical asymptote, and there is no horizontal because it continues to kind of go upward like that. Okay, so they're inverses of each other, but these are considerations you have to come up with. And remember, the easiest way to find, or at least to be on track to find a vertical asymptote, is get the domain of that function. Once you get the domain, you're in a good position to see exactly where this graph doesn't exist, and maybe there's a hole in the graph, but more than likely it means it's going to be a vertical asymptote. If you want to know horizontal asymptotes, that goes in with the stuff we just learned recently, where you take that function going to infinity and negative infinity and see what we get. Okay, so there's where that L'Hopital's rule that we just did, that's where we're going to find more asymptotes. So when we graph it, you see they have this final version here. A lot of this is not going to be different, but there's going to be some additions. What's going to happen? So we're going to look at the function. Always look at the original function, get the domain, get the intercepts, and get asymptotes. Now, keep in mind, when I say the asymptotes, I mean look and see that we're going to learn a little bit more today in this lecture, but see if there's horizontal or vertical ones right there, and then we're going to learn about another type of asymptote as well, but that's all going to happen here at this step one. Then we get into our calc part, where we're going to take the derivative, and remember how we do that. Partition numbers, we get that by setting the derivative equal to 0 and also finding the domain of that derivative. Where can it not exist? And then we do our sign chart. We try to see what is a max and a minimum. And if you've done the domain correctly of the first step, you'll know if it's an actual point or maybe it's just an asymptote. We're not sure, but that's how you can tell if it's a local max or min. Okay, then we do the second derivative. And we do the same kind of procedure. We're going to find the partitions. Well, to do that, get the derivative, and then also set the second derivative equal to 0. And then that'll tell you, when you do the sign chart, where it's concave up and concave down, and where our inflection points are. Then you put all of those together, and we get our graph. And a lot of this you kind of you're going to do this anyway, but get your asymptotes on the sheet. And once you have your asymptotes, what that does is, if you know them, that gives you like a framework, a backbone of this picture. It makes borders essentially, and then your job is just to fill in the rest of it. Okay, local intercepts, those are your supposedly easy points. Get your maxes and mins, inflection points, and then use the information about when it's increasing, decreasing, when it's concave up or concave down, all that stuff, and then you get your picture. And the last part is common sense for everything. you're going to get some of these problems where you're not always going to have a bunch of maxes and mins, or even many intercepts or inflection points. It just, you've done all the steps, but you don't get a lot of information. You can always go back and plot additional points. And remember, when you do that, you go back to that original function and you just plug in some x values. Okay, so I'm going to walk you through how they do this problem here. We're going to graph the equation f of x equals x over e to the negative x. All right, now the domain is all real numbers because remember, it's kind of a clunky problem, but this is exactly the same as saying f of x equals x e to the x. Okay, everyone see that there? It's just taking that negative x power and moving it upward. So this is probably a preferred form, and you'll see how we do the next part. So the domain is all real numbers. Just by looking at this function, there are no numbers that will make our denominator 0. There are no numbers that are inside of a square root, so all real numbers is the domain. Remember, that's the default domain, unless you get things like I just mentioned, a square root, negatives under the square root, or a 0 in the denominator. X and y-intercepts. So first step, plug in a 0 for x. That's going to tell you your y-intercept, and sure enough, you get 0 times 1, you get a 0. That's your x-intercept. Set this whole thing equal to 0, and when you set it equal to 0, well, x is 0, e to the x is 0. That's never going to happen. So basically, you only have one point of crossing the axis that's right there at the origin. Okay, now we look for our asymptotes. And you see here, we're going to see what happens to the left. We say, what's the limit of the original function as x is going to negative infinity? Well, what happens is you get a negative infinity on top. You get a positive infinity right here. And that would have been, so it's going to give you conflicting accounts here. So you get infinity over infinity. Now, if I plugged in the negative infinity to this, that I rewrote it, you would have gotten the same thing. You would have had a infinity on top, you would have an infinity on the bottom. So they sort of are giving you two different messages. So we have to figure things out. So we do our L'Hopital's rule, which remember, indeterminate form, infinity over infinity, take the derivative of the top and the bottom. So that's why you can't really do L'Hopital's right here. You can when it's a fraction. So that's why it sometimes is better to leave it this way. But know that they're the same thing. And when you're solving, you want this one on the right. When you're using L'Hopital's, you want this one on the left. So we take the derivative of each. You get a 1, you get a negative e to the negative x. And now when you plug in negative infinity, you're going to see this becomes a big number. The negative and the negative cancel off. So you get negative e to the infinity, which is negative infinity. And that's on the bottom, which means our fraction's going to 0. Okay? So that's what we end up having here in this particular case. We get a 0. That's saying as your graph goes far to the left, so if I have an xy axis right here, I know as we go far out this way, I don't know where my graph is going to be, but it's either going toward infinity that way, or 0 I mean, or that way. It's something that we know is coming closer and closer, so that is my horizontal asymptote. We know y equals 0 is the place that's going to be the horizontal asymptote. Okay, now technically you should check it going to positive infinity the same way. What happens is you go to the right. So if you were to do this same problem, you're going to get here. You're going to get infinity times infinity, and it looks like this one, where is it at? They don't show it here, but this is going to be a little different case. And let me show you this. Since it did not come up, let me write this. You want to consider both sides. So let's look at this one. When you plug it into here, you get infinity times infinity. That's going to tell us. So on the left, we're going towards 0, but on the right, we're shooting upward. Okay, and that's what's going to happen. As x gets bigger and bigger, this entire function is going upward. So we end the right side at positive infinity. On the left side, we end at 0. Okay, and if you recall, that's kind of how an exponential function typically looks. You're going to have one side that goes toward an asymptote. It doesn't have to be both sides. So that's why I just wanted you to consider what happens as x goes to infinity. So check both positive and negative infinity. Treat it like two different limit problems. Okay, so now we've got all that information. We sort of have that tucked away. Now we look at the derivative. Derivative of the function is going to be the product rule here. Okay, so if x times the derivative of e to the x plus e to the x times derivative of the x e to the x plus, that's a 1 right here, so plus e to the x. And then now always try if you can to factor this out a little bit, just so you have the cleanest possible derivative. So this is what our derivative is. It's e to the x times x plus 1. Now why is it good to factor? Well, it's going to be for the next step. Okay, the first step though is check the domain. Looks like my domain is all real numbers, so I'm not going to worry about that one. But now is where we set this equal to 0. All right, so we get 0 equals e to the x, or 0 equals x plus 1. So there's my first critical number at -1. And remember back in the original problem, -1 is in the domain, so this is going to be a critical point, something. It may be a max, it may be a min, it may be neither, but it's something important. And then over here, there's no solution. No matter what you put as a power of on e, you're never going to get a 0. So nothing comes out of here. So now is where we got to do that whole thing of let's check and do our sign tests around -1. Okay, so that's our partition number, as you know. And we're going to do the sign chart. And let me erase my work here so you can just kind of see it. When they test numbers, test any number to the left of -1, test any number to the right of -1, and remember we're testing in this derivative. So I'll leave this derivative up at the top of the screen. Say we plug in -2, and when you do that, you end up getting a negative number. All you care about is what's the sign of the derivative. That's a negative on the left, and when you plug in something like 0 or 1 or 2 or 10, something here on the right, when you plug that in, you're getting a positive number. So that tells you your function's decreasing to the left of -1, increasing here. So if my graph is going down, then up, then we know this point right here is going to be minimum. So that's our next part. F has a local minimum at -1 comma negative e to the -1. And remember how they get that? That's back from the original function. The original function, that's what we're plugging into. So let me just go back a couple steps just so you can not forget. There's my original function right there at the top. We knew -1 is going to be a local minimum. So what do I do to get the actual point? I plug in -1 right here. And that's how they got the answer that you saw. Okay. So let's just kind of fast forward back to where we were. All right. There's that -1 comma 1 over e, -1 over e, or negative e to the -1. And if you need to get a decimal to plot it, go ahead. But the exact point is right there. Or like I said, you could even say this. That's even better. Okay? So now we know it increases to the right of -1. It decreases to the left, which they didn't write, but it decreases to the left of -1 as well. Okay? And we have our relative local minimum. So now we find the second derivative. So go back to where the first derivative was, which is this one. And notice they did the product rule. If you went and FOILed this back out, you would have this, and you're still going to have to do the product rule right here anyway. So it doesn't really matter. Sometimes if you distribute it out, go away from the factored form, sometimes that makes it an easy derivative. But in this case, no matter what, you're going to get the same answer, but you have to do the product rule. So remember what they're doing. They're going to treat these as your two pieces. So they leave the first the same and take the derivative of the second plus the second times the derivative of the first. So that's how they arrive here at e to the x plus x plus 1 e to the x. And you can factor again, and when you factor out an e to the x, there's 1 plus x plus 1, so we get e to the x times x plus 2. All right, so the same procedure. You notice we're doing the same thing 3 times. Once for the function, once for the first derivative, once for the second. And the thing I'm talking about is you need to look at the domain every time. Well, in this case, it's all real numbers, so no big deal. And it was that for the other two. Then you need to set it equal to 0. So that's what the next step is. Set it equal to 0. And when you solve it, all you get is, put a 0 right here, the e to the x is 0 is no solution, but the 0 equals x plus 2 gives us this -2 as our second solution. Okay, and that's our critical point. That's our partition number. It may be an inflection point, it may not, but it's important. Okay, and that's what we need to do the sign checks around that. So we make our table right there around our sign check table around -2. We test both sides, and again, I'm going to remind you, we're testing the second derivative right here. That's what you're testing now. We're doing the second derivative test, is what they call it. So when you test it, you get negatives on the left, you get positives on the right. So that means it's concave down on the left, it's concave up on the right. So since they changed, this is an inflection point. So you need to go plug in that -2 once again back in your original function, and that's where you get -2 comma -2e to the -2. That's your inflection point. So it's concave up on the right, concave down on the left, and then now we put all this together. All right, so kind of look at what we have here. There's a lot that they didn't really explain, but this is how we got it. Remember, we had the 1-intercept right here. Okay, then we talked about the graph was increasing to the left of -1, increasing to the right of -1, decreasing to the left. So that's what we have. Then we knew this point was a min, so you can get the decimal, so we can plot this point. We knew this point was an inflection point, so we plot that with a decimal. We also knew, and it doesn't show it, remember, there's a horizontal asymptote as x goes to -infinity. And I told you earlier when we plugged in the limit to positive infinity, this graph was shooting upward. So we know a lot of details of what's going on. So now we just put it all together, and we know we're below this, so we shouldn't be crossing it. And we have to make the graph coming down, hit that point, turn upward, going through that origin, ending here. And the last part is to bend it to make the concavity. So we make it kind of bowl upward for concave up. That's all this. And then after this inflection point, you can't really tell, but it is concave down just slightly to the left of that -2. This part right here, see how it's just kind of bent down a little bit? That's our concave down. And this is our concave up. And this is our picture. Okay, so like I say a lot of times for this problem that has a ton of steps, each individual step is fairly easy. It's putting them together and doing like 10 steps in one problem. That's where it starts to get a little bit complicated and you can get some things going wrong. Okay, so the last part here we're going to talk about is what's an oblique asymptote. All right, so if you have your function and it's a rational function where it's a fraction, okay, and if the top degree, as in the highest power of the top, is 1 more than the degree of the bottom, then we can use polynomial division. If you remember that long division, where you can figure out what we have, and whatever you get as the quotient, that line, that's going to be an oblique asymptote. So what do I mean when I say an oblique asymptote? Here's what it is. If you have a function like this, and you learn the oblique is going to be, and we'll talk about how we get this 2x plus 1, what that means is graph the line at 2x plus 1, and that's a guideline so that as your graph goes over up to the right, it's going to wrap on this, and maybe the one on the bottom might end up like that. I'm just kind of paraphrasing what it might be, but it gives an idea of where your graph goes. It tells you a little bit about what's happening if you can find that. Now, there's a lot more steps to it than just plotting what I did here. You still have to go through all your derivatives, all your domains, all the increasing, decreasing, and concavity, but the oblique asymptote just helps you sort of finish your picture. Kind of like when we take the limit as the function goes toward infinity or negative infinity. If you end up getting, like the last problem, how we got the limit as we went to the right was positive infinity, this oblique asymptote will sort of clarify it. It'll give a little bit more specific, not just shooting upward, but maybe we'll have a guideline to that. Okay, so you'll see that as we go on. Let me show you here the next part, if I can get my cursor back, sorry. Okay. All right, so now we have our modeling average costs. So we have our function, Cx equals 5,000 plus 0.5x squared. X is the number of items produced, and they want you to use the graphing strategy to analyze the graph of the average cost function. Okay? So, remember what the average cost is. See if you figure out where they're getting this from, but remember, we talked about this a couple times. Average cost is the cost divided by the number of units, in this case, the items produced. So you take the original function, simply divide it by x, that's how you get the average cost function. So then they clean it up a little bit, that becomes 5,000 over x, and then in this case, 0.5x squared over x becomes just 0.5x. So now we're going to analyze this function. Basically, that means let's just do all those things that we just did. So you can't have a negative number of items produced, and of course, 0 will not work. So it's got to be, x has to be something bigger than 0. And that actually is good. When you have a smaller domain, that's less regions you have to check the signs on, less regions you got to test, less you have to graph. So believe me, it's better on that one. So now we get intercepts as none. Now, like I said, in these examples, they don't show everything, but if you plug in a 0, well, we already know you can't have 0 for x, so there's no y-intercept. Can there be an x-intercept? Well, I need to set the function equal to 0, and when I do, I believe I'm going to get a negative, but let me just show you. If we set the function equal to 0, okay, and what we're supposed to do is we're supposed to solve it. Well, I can multiply both sides by x, and I get 0 equals 5,000 plus 0.5x squared. And right here, notice I can't factor this because it's a square and a positive number. If this is the difference of two squares, I can factor it. But it's when it's the sum of two squares, there's no factoring, which means there's no solution for that as well. That's how we know there's no x-intercepts, nor are there any y-intercepts. There's just nothing. Our graph never touches that. And that's usually going to be the case when you're talking about these real-world modeling problems. You're not going to have a 0. You're going to have everything confined in the first quadrant, growing or dropping or whatever the case. So, yeah, we'd like to have intercepts because it gives us points to plot, but we can't make it happen. So now we look at the horizontal asymptote. And this case right here, what they're doing, and remember we talked about, well, they didn't talk about this, but I'll give you the shortcut. To find a horizontal asymptote, one easy way is you just divide the first terms, okay? So I don't like the fact that it's called a horizontal asymptote, I'll be honest with you, but it's to take the highest term of each, the numerator and the denominator. So going back to our function right here, the highest power on top is a 0.5x squared, the highest on the bottom is an x. You divide those two, and when you clean it up, this right here is not a horizontal asymptote. This is actually that slant asymptote that we're going to get to in a minute here. So there is no horizontal. Technically, like I said, the way you should do it is you should think about what's our limit as x approaches infinity, just to see if we get anything. And you'll find that you're going to end up, if you did L'Hopital's rule, you'll be having this go up to infinity. Okay, so that's one of two ways. Vertical asymptote, well, the line x equals 0, you can't have that. Remember, x cannot be 0. So that is a vertical asymptote that we're going to have. Okay, so oblique, this is that case where I think they actually do have these backwards. Now look at this. Yeah, okay. So what we're doing is, again, we're just trying to see what happens as x goes up to infinity. And what I want you to get out of this, and this is, call this like a third technique, if anything, it does work. And all you care about is what happens as x gets bigger and bigger and bigger. What's happening to my function? Well, what they did was they left it in this form. And look at this. As x gets bigger and bigger, we already talked about it, it's going to go up to infinity, but we have a specific. When x gets bigger and bigger, see how this x on the bottom is here? This gets to infinity. This fraction right here basically becomes 0. It becomes nothing. Okay, so I'll take that fraction. Let's just call that a big 0. What matters, what drives our problem is this, and this is the actual thing that we're going toward. This is the oblique asymptote. So when you graph this function, this y equals 0.5x as a dotted line, and just know that as you go out to the right, you're going to be approaching that at some point. So we just kind of keep that in our back pocket for now. And and I'll say this, good and bad news, maybe I shouldn't, but it's probably the least important fact when you're graphing these functions. But so if you mess up one thing or you don't know how to do one thing and it's that, you're not really going to get the problem wrong because you can just go plug in points and get the pattern. But you're going to have problems where they're going to actually ask you, what is the oblique asymptote? So you got to go through this process a little bit here. Okay, so now we're going to analyze the derivative. So we take the derivative of that original function, and we end up with negative 5,000 over x squared plus 0.5. Now remember, they're not showing how this is done, but there you go. Remember, my original function was right here. It's 5,000 x to the negative 1 plus 0.05x. So when you take the derivative, that becomes negative 5,000 x to the negative 2, and then that one, the x just drops off. We have this. So how they went from here to here, we just got a common denominator. Make this x squared, so that's why we have 0.5x squared minus 5,000 over x squared. So remember our process. Once you get the derivative, find the domain. Now, one more step they did here. Factored out the 0.5. We had x squared minus 10,000, and then they did the difference of two squares on this. Okay, that would have worked in the next step. It didn't matter. But we want to check the domain, so we can't get 0. Well, that's not a big surprise because we already knew 0 didn't exist. We also want to set this equal to 0. So when you set it equal to 0, a couple things that happen here. We have our partition number at 0. Set each factor on the top equal to 0. We get x equals 100 and x equals negative 100. Well, we throw out the negative 100 because we already said we can't have negative numbers. So my partitions are 0 and 100. So we set it up, and again, remember we talked about this a week ago. Why is this a critical number? Well, it's simply because partition numbers are what you start with. If they actually exist in the original function, then they're going to be critical numbers. Okay, and I bring that up because you're probably going to get asked that question a couple times in the homework. So this is how we know. 0 is not part of the original domain, so it can't be a critical number. 100 is, so it is a critical number. That doesn't mean it's a maximum or minimum. It could be neither, but it has a possibility. Okay, so now we set up our table here, checking for signs. Pick any number between 0 and 100. It doesn't matter what you plug in, but you have to plug it into the derivative. And if you look at this up here on the top, it could be any of these. These are all the same equation. They're all the same derivative. So plug the number 1 or the number 99 or the number 50, anything between 0 and 1. I'd plug in a 1, and it looks like we clearly get a negative, so it's decreasing. Now we plug in something above 100. I'd plug in 101, and I actually think the best one to plug in is this one right here. And it won't really matter too much. I'm trying to look at these. Yeah, this is probably the best one because now you can play the plus minus game. If you plug 101 into this parenthesis, you get a positive. If you plug 101 into this parenthesis, you get a positive. So we have a positive, a positive, a positive, and a positive. All positives, that's how you know this is positive here. So our function, it's decreasing up between 0 and 100. It's increasing after 100. That means, by rule, if it's decreasing then increasing, this 100 must be a local minimum. So we plug in the 100 to the original function, and we also get 100. So the point 100, 100 is a local minimum. Now we find the second derivative. Same thing. Take the first derivative. Right here. All right, make this a negative 2x to the negative 2. When I take this derivative, this 0.5 is gone, and now we get a positive 10,000 x to the negative 3, which becomes this. So once again, set it equal to 0. X can't be 0. Well, we already knew that, so that doesn't exist. And then everywhere else, there is no, when we set it equal to 0, we get 0 equals 10,000. There is no solution, so there is no inflection point. There's no more critical points. The only partition point is at 0. So what that means is, and they're not going to show this, but if we were to do our sign tests, well, I test at 0, this is all going to be the same. It's either all going to be concave up or all got to be concave down. So you still want to test a point. Well, let's test x equals 1, the easiest point. So I'm testing it right in here. And you notice I get a positive, and that's how they have this conclusion here that your second derivative is positive everywhere. So that means this graph is going to be concave up always. The whole time it's going to be concave up. Now keep in mind, we learned it was going to be decreasing then increasing. it switched increasing, decreasing, but the concavity, it is possible it can be concave the whole time. And you'll see in a second why. And you know because what the original problem looked like. So it's concave upward everywhere from 0 to infinity. No inflection points. Now we're going to sketch the picture. So look at this picture and see if you can get where I get everything from here. All right. The the blue is our picture right here. Okay, so this is the original function. It's the blue. Remember, it was decreasing until we got to 100, and then right here, and then it was increasing after. It's concave up the whole time. We have a local minimum there. We have a vertical asymptote at 0, which is why this thing is going up and getting close. And our last part, remember this green oblique asymptote we found? That tells you that as your graph goes further and further out, it gets closer and closer to that green line. And that's just helping refine our finish right here. Okay? So that's it on how to graph that. That's all we're looking for. Now, the things they're looking for is what's the marginal cost of the function? Well, that's the derivative of c. And they have just that plain x right here. And let me take you back a few slides to show you. Remember where the cost was? Sorry, right here. Somewhere right up here. Okay. Just the cost. Okay. To get that c prime, remember what they do. Take the derivative. Well, that's 2 times 0.5, which is 1. That's how they got this x right here. That's how they got the derivative. So that marginal cost function is, show it, sorry, c prime x is just plain x, and that's what you see right there. Okay, so important economic principle, you can kind of see minimum average cost always occurs when the average cost is equal to the marginal cost. And that's an important extra little fact there. If you can find the derivative of the original function, and then remember the c with a line over it was our average cost, the function divided by x. And then if you found that local min or max, it's always going to intersect it right there. Your functions always intersect at that point. So it's kind of a nice little extra helper that you can get here. All right, so that's it for the lecture. Like I said, it's not a lot of slides, but I want to get right into this assignment so you can see some of these problems and understand what needs to be done. Okay, let's try this again. Give me a second. Let me get this to load here. Okay, there it goes. So, let's see. We are at homework 11 already. Let's do section 4.4. Let's just pick up and do these last few. Now, I'm going to go through some of these, and you're going to see they're going to be, some of them are going to have a lot of parts if you haven't already gotten there. All right, some of these are not too bad, but then there are 2 or 3, I'll tell you, that are going to be a little time consuming, but it's one of these where they're not difficult. It's just a lot of tedious work, okay? So in this one, we want to find the domain and the intercepts. Well, this isn't so bad. I can already look at it and say, to get the domain, I set the bottom not equal to 0, which means I cannot have 4. So my domain is going to be all real numbers except that positive 4. Every number except 4. And check it. We're good on that one. Okay. Part 2, let's find the intercepts. So process number 1. For the y-intercept, we find f of 0. Looks like we have a negative 13. Now the actual point is negative 0 comma negative 13. Now, oh, sorry, that's the y-intercept. 0, negative 13. They're actually asking for the x-intercept first. So let me go do that and we'll come back. So the x-intercept is set the whole function equal to 0. That's a 52 over x minus 4. Now remember, Can't say this enough. When you have a fraction equal to 0, all that matters is the numerator is equal to 0. If you wanted to see it algebraically, I would just multiply both sides by x minus 4, and you arrive at this point where I am now. Now I'm supposed to solve for x, but there is no x to solve for, so this is a no solution. There are no x-intercepts in this picture. All right, now x-intercepts, you can have 1, 2, 3, 4, 5, or you can have 0. It is very possible to get none of them. And just think of a parabola that's above the x-axis. It never hits the x-axis, so you may have none. But if it was slightly below and pointing up, you may hit it twice. Certain functions could hit the x-axis many times. Sometimes they don't ever hit it at all. So our y-intercept, like I said, the point is 0, negative 13. If I'm asking for this like in class, I like the coordinate. I want you to know it's the point, 0, comma, negative 13. But make sure you read what they're asking for here. They just want to know what the y value is, so you say negative 13. And that's it for number 31. Okay, so let's look at number 35. Okay, so in this case, they give you all this information and they want you to pick the right graph. Okay, so I love these exercises because they really get you to understand what you're finding. So we've been working on all these steps of how to find first derivative, second derivative, positive, negative, inflection, all that stuff. But now it's a matter of let's apply it. What did we find? So I'm going to go through one at a time and just kind of make sure we're all on the same page and understanding what this says. This right here, this first bit, that is just literally giving me the point negative 12, negative 2. Okay, that's a coordinate. I'll save that for later. Now I could look at each of these graphs and I'm going to eliminate anybody, but I can just look at one of these. Let's look at this one right here. Do I have the point negative 12, negative 2? I do have it on this one, so it's good. On this one, do I have it? Yep, right here. And on this one, do I have it? Yes. So it didn't really help us, but we're going to save it for later. And just like this next one, we have the point 0, 0, and we have the point 12, 2. Now, just by eyeballing these three red dots, they look the same in all three of them, so that doesn't really eliminate anybody. But that's kind of the name of the game. Are we going to eliminate the right things? Now we talk about this. This is where our derivatives come in. When they tell you that f prime of x is less than 0, you got to remember, first derivative means increasing, decreasing. So if it's less than 0, that means your derivative is negative. It means you're decreasing from negative infinity up to negative 8. Okay? And also from 8 to infinity. And then the last part of that is in between from negative 8 to 8. That's not a point. That's a range, an interval notation. It's increasing here. It's decreasing here. So this is what I know. My graph is going to decrease down to negative 8. It's going to hit negative 8 and turn upward to increase. Then it's going to hit positive 8 and it's going to go down again. So now I'm going to look at these pictures and see if I can conclude any of that. Yep, decreasing to negative 8. Supposed to increase in the middle here. This looks like it's decreasing the whole way through. So I can already throw out part A. Let's look at part B. Decreasing, no, that's not decreasing up to negative 8. That's an increasing, so that's out. This should be my only choice, so let's just kind of keep this over here. It's decreasing to negative 8. It's increasing after from negative 8 to 8, and it's decreasing after that. So that does hold up consistent. So I pretty much know this is my answer, but I want to make sure you all see the rest of it. Here we have a second derivative less than 0, which means it's concave down, because it's negative, less than 0, concave down on the left of negative 8, concave down between negative 8 and 0, then it's concave up from 0 to 8 and 8 after that, and sure enough, this is concave down, this is concave down, this is concave up, and this is concave up, and nothing happens right at negative 8 and 8 because those points don't exist. Now, they didn't tell us the original picture, but I can just tell right now from this, at least, nothing's happening there. There's no points, there's no inflection, there's no maxes and mins. I do know there's an inflection point though right here at 0. Okay, that's the one spot where it goes from concave one way to concave another. So 0, 0 is clearly an inflection point. And then last, they did tell us vertical asymptotes and horizontal asymptote at y equals 0. So as you go out far left, that's our graph right there. All that description is telling us we have the graph of C. Okay? So that's the deal here on these little set of problems, these handful. They're just giving you information. You have to know how to translate that. Greater than, less than. Just think positive and negative. Okay, now I'm at 39. Now I'm going to point out something. See if you catch this. There are 10 parts on this problem. All right? Lots of steps to do, but we're going to do them one bit at a time here just to make sure you're getting this and seeing what needs to be done, because you're going to have a handful of these. So first step, here's my equation. And I can tell you right now, I know we're going to run out of room, but we're going to do everything we can to show it all. Okay. So first question, and you should have this procedure down, but what's great about these 10 parts, they're going to go walk you through each, excuse me, each of the 10 steps. Excuse me. Well, the first question is, what's the domain? Well, I see no roots. I do happen to see a denominator if I put this down to the bottom, but what you have to remember is there's no way that denominator can be 0. Therefore, my domain, it appears it's going to be all real numbers. Cursor down here. Okay, all real numbers. And what I like about this, even though there's 10 parts, you get to check each step of the way. So if you get something wrong, you're not going to go into an abyss here. You can fix it before you go on to the next part. Okay, this can get frustrating though if you try it too many times. I know the problem will reset, and you might do 6, 7 parts, get it wrong too many times, and then you got to start over. So just take your time on this. Find the x-intercepts. All right, so I take the original function right here, and I want to find the intercepts. And remember the rule to find intercepts: you set the whole function equal to 0. And then you set each factor equal to 0. So I set that equal to 0. I set this equal to 0. And no matter what I plug in for x, I'm never going to get a power of e to be 0. So that's out. But I do know we have a 0 here. So there's my x-intercept. I have one at x equals 0, 0. But we just want to know what the x value is right there. Okay, so that's it for second part. Now we want to find the y-intercept. Now I already know one of them because I have the origin point 0, 0. But the other step is, it's the easier one, I believe. I usually do the y-intercept first, but they're asking you to do the x-intercept first. But the y-intercept, as you saw from that last example we did, or a couple problems ago, that means to find the y-intercept, we're going to find f of 0. So 5 times 0 times e to the essentially 0. 0 times 1, we get a 0. We get the same origin point. We knew this is going to be there, so we didn't really have to do the work, because there's only going to be at most one y-intercept, because otherwise there would be, if there's 2 y-intercepts, there will be a non-function. So we only have the one. So if you happen to get a 0, 0 as one of your x-intercepts, remember, you can get more than one x-intercept, but if one of them happens to be 0, you automatically know your y-intercept is 0, and that's it. Okay, but I still did the work just to show you. All right, so now we look at horizontal asymptotes. Okay, there's a couple ways to do this one here. We're going to experiment. We're going to see how finicky they are here. But the way I like to look at it is, what happens as your graph goes to infinity? And then I also want to know what happens as your graph goes to negative infinity. What are you getting? Okay, so when I do this first one, if this is my function right here, which is, if I bring it down, it becomes a positive 0.4. I get infinity over infinity, so that's going to tell me something weird is happening there. That's one of our indeterminate forms. So what I need to find out is, let's do a little L'Hopital's rule on this one, just to see what exactly is happening as we go far out to the right. So I keep the original limit going to infinity, and I'm going to find out the derivative of the top and the bottom. Well, that's a 5, and that's a 0.4 e to the 0.4x. And now when I plug everything in, I get 5 and I get infinity, which tells me I get a 0. So what that means is, as you go out toward positive infinity, as your x goes to positive infinity, your graph is going to 0. I don't know if it's from the top or the bottom. I know, though, that there's a 0 is what our horizontal asymptote is. Okay? So if I plug that in, now there may be more than one, so I'm not going to answer this yet, because what we have to do is we need to check from the other side. Remember, what's the limit of the same function as x goes to negative infinity? Okay, and sure enough, I get negative infinity, and on the bottom there, what am I going to get? I'm sorry. When I put this down, it's a positive 0.4x on the bottom. So this thing becomes e to the negative infinity, which basically brings it back up top. So we're going to get an infinity times infinity. So as we go to the left, it's going to go to some kind of infinity. It looks like it's going to a negative infinity. So it's going to go downward as we go to the left. So what that means is there is no other horizontal asymptote. A lot of times it might also be 0, the same on the right and the left. Many times you're going to get the same, but sometimes you're going to get a couple of different cases. You'll see some examples where maybe one part of the graph is going to go toward like y equals 7, and another part on the other side might go y equals 1, go toward that. So you just want to check both sides just to see what's going on, what's happening with these asymptotes. So it looks like I've got just the one at 0. And what do they tell me? What am I doing wrong here? X equals 0. Okay, I think I found the mistake. I got the right answer. Again, you see me do this because I'm trying to rush through this. I apologize. They want you to type an equation. So remember, vertical asymptotes are always x equals something. Horizontal asymptotes are always y equals something. I hope that's the only thing we're missing. And now we have it. So we were right with the 0. We just had to be that. Now they want vertical asymptotes. And remember, vertical asymptotes go directly off of what your original domain was. Well, if I had a domain of all real numbers, there's never going to be any vertical asymptotes. So in this particular case, we should have none. Okay. If it was, like x could not equal 4, x can equal 7, those are most likely going to be your vertical asymptotes. All right, now we need to find out where it's increasing or decreasing, which means now it's time to do some derivative work. So when I do this, remember, I'm doing the product rule, and you could bring this e to the 0.4x down to the bottom and do the quotient rule, and you're going to get the same answer. But I'm going to stick with the product rule, and I'm going to call this my first and my second. You got to deal with that 5 somewhere. You either put the 5 with a big parenthesis around everything, or you just incorporate it to one of the pieces. And I found that's what's usually going to be easier. So I leave the 5x by itself, and then the derivative of this is e to the negative 0.4x times negative 0.4 for the chain rule. And then we leave that as it was and multiply it by the derivative of 5x, which is just 5. Okay, and this next part is important. You want to clean this up the best you can. Okay, like for example, I can factor out an 5e to the negative 0.4x out, and what I'm left with is a negative 0.4x plus 1. And I can clean that up even more to be negative 0.4x plus 5 times that all over e to the 0.4x. So these are all just different versions, different ways to look at this. Okay, but here's what we have to do. Same thing. Check the domain. Well, my domain is still all real numbers, so I don't have to worry about any points out of there. But now I need to check it. Where is this graph equal to 0? So set equal to 0 at the top. Remember, it's only the numerator. The 5 is a constant, so ignore that. So it's just where does this equal 0? 0.4x equals 1, and x equals 1 over 0.4. And that's going to be what, a 2.5? 2.5, 5/2, however you want to call it. Okay, so now we're still not done. We have to figure out where is our graph in terms of increasing or decreasing. So I have all these derivatives here, here, and here. I don't know, it doesn't matter which one you use, but you need to test some points. So I'm going to test, let's test a 0 and let's test a 3. That's what these pink numbers are. These are the ones I'm testing. So I'm going to plug in 0 to one of these. It doesn't really matter which one. And I'm going to kind of stick to that one right there because I can kind of do that in my head. If I plug a 0 in there, I get a 5, I get a 1, I get an e to the 0. Either way, it's all positives, so there's where my function's increasing. Okay, if I plug in a 3, all I'm looking at is what are my signs. I get a 5, I get a negative 1.2, so that's going to be negative 0.2. And on the bottom, I'm getting e to the 1.2. What matters is it's a positive 5, it's a positive denominator, and it's a negative 0.2. So that's negative. That's how I know my function is going to be increasing or decreasing. Now, just kind of look at a few things here. Okay, so we know it's increasing and decreasing, and I'm just looking at how to type in our answers. They want this in interval notation. They want you to use integers or decimals, so we can use that 2.5. It's increasing from negative infinity all the way up to 2.5, and it's decreasing from 2.5 all the way up to infinity. And cross fingers, yep, you got it right there. Okay, so that's it for that one. I'm going to clear this out. You see, we've done a lot. We're already 6 parts through, so we're at number 7. Local max and min. Now remember, it was increasing up to 2.5, then decreasing after. That means that's going to be a local maximum there at 2.5, and there's no local minimum. Look at all your choices. There's neither any of them. A choices, you have a max and a min. C is you have a minimum and no max, but ours is we have a max and we have no minimum. And the x value is all they want, so we type in that 2.5. All right, find the intervals where it's concave up or down. So we have to take that derivative again. And I did erase that, which I should have left that on the screen. So let's just do that again real quick. All right, so remember, okay, so you see here, back to our derivative that we just used, our first derivative. When we're talking, they're asking now about concavity, so we have to find a second derivative. So you need to take the first derivative and basically get the derivative of that. Now, if you look at all the versions I have up on the screen, I believe this is going to be our best choice to find the derivative of it. Okay, now I could do the quotient rule of this one I'm erasing, but I'm going to just stick with this one. Again, it doesn't matter. You're going to get the same answer. But I'm going to treat this again like a product rule. This is my first, that's my second. So the second derivative will be the first as it is times the derivative of the second, well, that's just 0.4, plus the derivative of the second as it was times the derivative of the first, so that's going to be a it's going to be a 5e to the negative 0.4x times the negative 0.4. And again, a lot of these steps that you're going to have to do, and you can't cheat them out of them, is you have to clean this up a little bit. You have to use your algebra. So 5 times negative 0.4 gives me a 2e to the 0.4x for that first term. Over here, I'm also getting a 2e to the negative 0.4x. It's just times 0.4x plus 1. And I can factor out. And the factoring is really just to make your life easier for the next step. And make sure everybody sees where I got that 2 from. When I factor out of here, I factor out in 2e, it's the whole thing, so I'm left with a 1. When I factor it out of here, I'm left with this bit, so I combine those two, and that's how I get the plus 2. So we now have to set this equal to 0. And all I'm really looking at is this second piece, because when I set the e to the negative 0.4x to set it equal to 0, I'm going to get the same answer of nothing exists. So we get 0.4x equals 2. Looks like x equals 5. And now I have to check concavity around 5. Okay, so look at my second derivatives here. Let's test 0 and 6. I always try to pick the easiest numbers. When I plug 0 into this second derivative, it looks like I get 2 times e to the 0, which is just 2. And when I plug a 0 into that parenthesis, I get a 2 times basically 1 times a 2 in there. It gives me a positive number. All I'm looking for is the signs. We're concave up right there. Okay, now I plug in the 6, and again, just looking at the signs that you get. We get a 2, we get an e to the negative 2.4. Even though it's a negative power, that's positive, but what do we get in the inside? We get a negative 2.4 plus 2, so that turns negative. That whole thing becomes negative, so this is going to be concave down. And that's how we answer our question. We're concave up all the way up until 5, and then we're concave down everything after 5. So between negative infinity and 5, and then concave down from 5 all the way to positive infinity. And what I missed wrong here? Make sure I'm answering interval notation, decimals. You did get that right. Let me make sure I didn't mess up. Okay, I did see it. I tried to do one thing. Let me see if I can highlight the fix here. I'll do it here in green. Okay, so when I take this 5 times the negative 0.4, it is 2. It's supposed to be a negative 2 right there. Same with this one. This 5 and this negative 0.4, that's supposed to be a negative 2. So when I factor them out, all it changed was I factor out a negative, and then this part still stays the same. That's good. Okay, so we have the parenthesis, and then we have the 1. So that one's good. It's just a negative out front, and what that's going to do is that's going to turn everything around, because I still solve and I still get the 5, but now when I test, because there's a negative out here, when I plug in a 0, I actually get a negative in that first region. And then I get a positive in the second region. So that was, because of that one little negative, everything gets swapped around. That was the one part. So concave up is going to be from 5 to infinity. And concave down is going to be from negative infinity up to 5. And I believe that was the only mistake. Yeah, that's all it was. Okay, so that's how we got that part right there. Now we need to look at the inflection points. Remember, if the concavity changes like it does here, then that point is an actual inflection point. So we have to plug 5 into that original, and they don't want to know the actual value of the point. They just want to know that we have an inflection point at 5. So that part is good. And then now, after all that, we have to come up with a picture. That's what our part 10 is. Okay, so we're looking at all this here, trying to find out which of these graphs works. So I'm going to keep pointing up at all this information we found here. Okay, everything we found. Domain is orbital numbers. So these all look like they fit that. X-intercept and y-intercepts at 0. Well, looks like these are touching at different places. Not B, not A. Origin is our point. Remember again? X-intercept and y-intercept are at 0, so it's got to be either C or D. Asymptote. We found it has a horizontal asymptote at x, y equals 0. Well, it definitely has one over here and over here. But if you remember how we worked it out, we found it when x is going to a positive infinity, the function's approaching 0. So it looks like it's going to be this one right here. This one is the opposite way. But we'll look at some more things here, and they're all going to kind of satisfy it. No vertical asymptotes, and that is actually what we have. If you look at these closely, like this one, it's not actually touching, it's not stopping where it's going down, but it still continues to go out to the left. Same with this one going out to the right on C. Okay, let's look at decreasing, increasing. Well, it's increasing all the way up to 2.5 and decreasing after. Well, this is almost, but it looks like it's negative 2.5. It's got to keep going past it, increasing and then decreasing. This one increases at 2.5, decreases after. We have a local maximum at 2.5. Sure enough, zoom in if we have to. Right here at 2.5, there's my local maximum. And then concave up from 5, 1, 2, 3, 4, 5 on. See, it's slightly bowed upward and then definitely concave down on the left. And an inflection point at 5, there's our picture. Only one that works. Okay, 10 parts, lots of work, but like I said, each one individually is not too bad. Okay, so at this point, let me just see what else we have here. 43, I believe, is going to be the same kind of thing. You got a handful of these, and I'll admit right now we probably have too many here, so don't get too caught up on them. But the process is going to be the same every one of them. Follow the steps. Find the domain by looking at it. In this case, I can tell you it's going to be everything except for 1 and negative 1 when I factor out that equation. Okay, factor out the denominator. Okay, go through the process though. To find the x-intercepts, you set the entire function equal to 0. I don't think they're going to have any in this case. Okay, to get the y-intercepts, you find f of 0, and it looks like I get 2 over negative 1, so it's going to be y equals negative 2. I don't expect you to do them this fast, believe me. I want you to go through the work. I'm just reminding you how to do them. Horizontal asymptote, this is the one where we're going to set the function equal to infinity as time goes on. And you'll see something interesting, and I want you guys to try this out. When you set this equal to infinity, x is equal to infinity, you're going to get infinity over infinity. You do L'Hopital's rule, you're going to get infinity over infinity again. You do it one more time, and you're going to get a horizontal asymptote at y equals 4. Okay, because as we go right to left, we're going to be approaching the number of 4. When we do a vertical asymptote, well, remember we already talked about where it doesn't exist. The leftmost asymptote, and they want equations. X equals negative 1 is one of them, and the other one, the places where x doesn't exist, is at positive 1. We got that one, yep. Where is it increasing, decreasing? Now this is the part I'm going to let you work on this one. We have to use the quotient rule. We have to set this up. So let me just make sure we're all on the same page here. So I'll do this one, and then I'm going to go on to the next problem. But looking at my problem right here. Now the good news, like I said, is it's all the same procedure. The 10 steps we just did, we're doing now. Process on this part, part 6. Find the derivative. Now that part may vary because certain problems are more difficult than others, but we're going to do the quotient rule here. So when I do the quotient rule, remember we set the bottom and square it. The quotient rule says you take the denominator times the derivative of the top minus the top, and use parentheses, times the derivative of the bottom. And you need to clean this up a little bit. Okay, so I'll come back to the problem. I just want to give us a clean paper to write on here. So as I'm doing this, the denominator is not going to change much at all. Don't multiply it out. Don't do anything else. You can factor it, and it becomes x plus 1, x minus 1 twice. So it's x plus 1, x minus 1 squared, each squared, or you could have left it how it was. For the top now, I actually have to multiply this out, and then I have to multiply this other one out. Okay, so you see what I did here? Distribute the 8x, so I get 8x cubed minus 8x. Distribute the 2x, and I'm distributing the negative. So treat it like I'm distributing a negative 2x. So that's how I get a negative 8x cubed and a negative 4x. And then from there, still all this algebra, well, I am now just trying to clean up that numerator as best as I can. Okay, now I'm lucky in the fact that these two things cancel, and then I'm left with just a negative 12x. So now it's simplified as much as we can. We find the domain, well, you still can't have negative 1 and positive 1. Okay, so x cannot be negative 1. X cannot be positive 1. Those are important because remember, those are partition points. They're not going to be maxes and mins because they don't exist, but they are going to be things that we need to check around when we do our partition. Also, I have to set this equal to 0, and you see here I get just the top is what I have to be 0, so I get x equals 0. That's a potential critical point. So when I do the testing, here's where I have to test around all the partition points, negative 1, 0, and 1. So I have to test points. Now I'm going to show you a little shortcut here. When I test points, I'm testing them in the first derivative, right here. Okay, now the factored form makes it good because I want to show you a few things. See this bottom piece that's squared? It does not matter whatever x is, that's always positive. Same with this one. The only thing that matters is what I get when I test up here. That's the whole driver to see if my derivative is going to be positive or negative. So when I plug in, say, negative 2, it's going to be negative 12 times negative 2. That's going to be positive. When I plug in, say, negative 1/2, again, the bottoms are going to give me a positive, but the top is going to be negative 12 times negative 1/2. That's a positive. So we're increasing here, we're increasing here, and we're going to be decreasing here and here because, again, I'm plugging in, say, 1/2. 1/2 times negative 12 gives me a negative 6. That's negative. Plug in 2. 2 times negative 12 is negative 24. That's also decreasing. So we're increasing, increasing, decreasing, decreasing. And that was the question that they were asking here was, I'm trying not to let everything get erased, but where are we at? Where is the function increasing on? Well, I know it's going to be increasing from negative infinity up to negative 1, and then also from 1 to 0, oh sorry, negative 1 to 0. And of course I put it in the wrong spot. Increasing here, also decreasing from 0 to 1 and from 1 to infinity. Now notice I have to put this comma there because at negative 1 and positive 1, remember the graph doesn't exist, so it's neither increasing nor decreasing right there. So you can't just say from negative infinity to 0. Even though that's pretty close, you have to omit that negative 1 when you plug in these answers. So that's how I got that part. And then local minimums, remember, mins and maxes. Number 1, because these points don't exist, there's no way they're going to be maxes and mins. Don't even look at them. It's potentially right here, and remember, as long as it goes from increasing to decreasing or decreasing to increasing, which it does, so at 0, we have a local maximum because it's increasing all the way up to it, and that's it. That's my last one, no minimums. Okay, so like I said, I'll save the rest for you on that one if you look at this problem. The next part is the concavity, and what you need to do is you need to take that first derivative that we got right here, and you need to go find the quotient rule of that one. Now, I'll give you an advice on this one. We take the derivative of the derivative. This is the cleaned up simplified form. For finding the second derivative, I would revert back to this, where it's x squared minus 1 squared. It doesn't matter, because when you do the quotient rule, it's now going to be the fourth for the second derivative. Okay, but when you do the bottom times the derivative of the top, top minus times the derivative of the bottom, you got to deal with that one right there. That's a lot easier than all this stuff right here. Okay, so that's my advice on that one. So, like I said, go through these. You should be fine on what we have. As you can tell, there's not a lot of homework problems, but there are tedious ones. They're going to take a little while to do, so just make sure you do each of these. Okay, so just going to glance over the last couple to make sure we're all on the same page, and I don't know where it went. There it is. Okay, 47 has only one part. They have that cost function. Find the oblique asymptote. So remember, the average cost function is this function divided by x. So the average cost function is all of this, the 10,000. Let me do this with some more room. Okay, so average cost function, that's that function C with a little line over it. That's going to be the original function you had. So 10,000 plus 91x plus 0.03x squared. All you do is you divide it by x. So we get 10,000, right? 10,000 over x plus 91 plus 0.03x is what that simplifies to be. Okay, and they're asking find the oblique asymptote. So the oblique asymptote is simply the original function cleaned up with it. You know, it's this, and they want you to do the long division of that. Well, guess what? We've already done the long division right here. And the idea of the oblique asymptote is it's the limit as x approaches an infinity. And once you have it broken down into this form right here, anything that has an x on the bottom, that thing is a big zero. So for my oblique, it's going to be y equals 91 plus this 0.03x. That's it right there. Okay? So the oblique for the average cost function is going to be that, I hope. No, what did I get wrong there? Infinity or negative infinity? Did I just type something wrong here? Is 0.3x. Oh, I know what I did wrong. Forgot to put the y. No, I didn't. Okay, not a live class, so at least some of you might have been yelling the answer. You see my mistake, I just didn't put the 0.03 in here. And now we got it. Okay, so I think that was the last one. Is there number 51? Okay, on that one, you have a few parts here, and I'll just kind of tell you that in going away here. They want you to write the expression as average cost. So remember, take the original problem, divide it all by n. Okay, so I can look at this right here and just know it's 1960 over n plus 200 plus 40n. Oh, no. Oh, I did get it right. Yeah, sorry. I didn't mean to put the c of n. It was already there. Graph the function that we just found in part A. So in this one, this is the one where you go through the process of let's find out what exists, what doesn't exist. We know we're not going to have any negative n's. We know from looking at this you can't have a zero, so there's a vertical asymptote. And excuse me, you can go through, you don't have to go through the whole part of finding all the first, second, third derivative. What they're trying to get you to see here is what is that oblique asymptote And remember that oblique asymptote is just simply this 200 plus 4n. It's like you get rid of this part and you just deal with what's left over. So if you think about how that line looks, that's what all these dotted lines are. Okay? So, excuse me. We're trying to see what we can graph that to be. And it's definitely not this one. And there's no oblique over here, so it's got to be one of these right here. And if I zoom in, you can kind of see, but you can't. It's not 100% clear. This is a little bit up there. Is that at 200? I don't know. This one is not there. It's at 0. If you remember this is the equation for a line. This is like your y-intercept. So that should be your piece right there that we're looking at. Okay, that's how we can kind of go to that one. And then what's the average cost per year minimum? And then we give you the hint. Frequent referred to as the replacement time for this piece of equipment. The average cost per year is minimum after how many years? So we're looking for the minimum. Now I can look at this picture. I can also look at that other idea, remember, where we make the marginal costs equal to that. Okay, so if I take this first derivative and set it equal to that one, or I can just take the derivative of this one and find out what it was. And that's probably the one that I'm going to recommend just because it fits more with what our theme is and it gives you that better practice. But I would go and take that derivative that we just found, okay? Because remember, this, let's see here, this function is the graph right here. So we're really looking for this bottom point right here. Anytime you want a bottom point, okay, there's two ways you can do it. The way I'm going to say to do it is take the derivative of that right there, and whatever you get for the derivative, set it equal to 0, and that's going to tell you the critical point. That's going to tell you what you get right there. It's going to take a couple steps, but that'll get you your answer. So try these out. Like I said, it's going to take some time. These are not quick problems. They are going to be a few minutes for a lot of these here. So make sure you give yourself plenty of time this weekend to do them. You know, I'm recording this on late Wednesday night, early Thursday. So by the time you see this, make sure you allot time. You know, don't think you can do 6 of these in one night on Monday night and then do the quiz. You really have to spend an hour here, an hour there. Try to do something on Saturday, something on Friday, something on Sunday, maybe Monday morning. Give yourself some practice. Give yourself some time. Okay? So work on those. If you have any questions, shoot me an email. And I'll record the next video and send you out this weekend here. So good luck on everything.